First of all, I'd like to thank organizers to giving me such very nice opportunity to stay and to give a lecture like this. And a few weeks ago, Callum Caulfield gave a seminar, and the subject of his talk is related to this. And I believe I couldn't attend his meeting, seminar. So if I would have some overlap, I'm sorry, I apologize. Otherwise, please listen to me kindly. Okay, so temperature front formation in stably stratified turbulence is the title. And I'd like to start with an old story about the motivation of my research. And it went back to maybe 30 years ago, well, something like that. And so vortices in stably stratified turbulence is a very naive question. And so we did some numerical simulation of box turbulence with stratification and showed some pancake structures. Meanwhile, so this is, I will explain later, but meanwhile, John McShomaz and Paul Biran, they produced so-called zigzag instability and showed some vortices. And later, these isolated vortices become a kind of pancake structures. So actually, their experiment is produced, well, actually, vortices are produced from large scales, which I will explain. And meanwhile, our simulation is pancakes also, but produced from small scales. So we have different, starting points, but we eventually presumably have the same structures in stratified turbulence. And we didn't understand why it is true or not, the same thing or not. So anyway, let me go back to a little bit briefly explain their experiment. So they had the salt tank, and they have a flip moved by stepping motor or something like that to produce dipoles, large-scale dipoles at the end of the tank, and introduced it towards the salt tank, which has a linear stratification. And this is an experiment photograph taken by maybe Sriren or something like that. I'm not an expert on experiment. But anyway, so originally they are just two vortex columns. But as time goes on, 7 seconds, 36 seconds, 75 seconds, 109 seconds, and 176 seconds. So rather slowly they produce such kind of structures. So this is a front view, and this is a side view. Also, by the way, please ask any questions if you have any questions. So these are very classical things, very famous. So everyone are familiar with this, I believe. So anyway, and meanwhile, so our simulation is starting from, it's a box turbulence, starting from initial energy spectrum with Gaussian random noise. And with certain initial spectrum and Reynolds number, microscale Reynolds number is around 80 for our simulation. And first we crank Navier-Stokes without simulation. So it's a decaying turbulence. So energy, kinetic energy decays in any event. But entropy, if it cranks up, entropy increases a little bit until a certain point to produce very thin worms. And we switch on stratification when there are many isolated isotropic vortices or something like that. Then we start the stratification. So as Brandt-Weissel frequency becomes bigger, Brandt-Weissel frequency, thanks to Bruce, who introduced a few days ago. So stratification becomes bigger, and we propose the kinetic energy times T to minus 1 as n goes to infinity, something like that. But we don't know whether it is true or not. I think there are open questions for stratified. So anyway, so this is a blow-up of entropy contour for our simulation. And so we had the so-called scattered pancakes. And if we blow up this one, it is shaped in a little bit tilted in the space, and arrows are velocity vectors. So velocity vectors are in horizontal directions. So these vortices shows very strong shear layers. So to explain the generation of pancake vortices, well, Andy Maeda and Groth, they kind of presented the theory using low fluid number limit model by Riley, Metcalfe, and Weissman, which has a double in the vertical velocity 0, and the horizontal direction is coupled. So, this one is linear advection diffusion equation, and Maeda and Grote used special initial conditions to have an exact solution. So this is a simulation which I produced from the equation anyway. So starting from columnar vortices, they produce pancakes, and they begin to move around. And as time goes on, so we had we observed the kind of wedge-shaped vortices. So anyway, so still it's a linear equation. We have such a interesting structures. Okay, so now so we still had the naive question. Are they the pancakes which are produced from large scale, and the other one is from small scale, are the same thing or different? And we try to do this Navier-Stokes equation again using Boussinesq approximation, as is already explained well by many people. So I think it's okay now. You're expert on this problem. So now theta, we use theta as a temperature fluctuation. Temperature fluctuation is a fluctuation from the mean temperature, and n square is a slope of the mean temperature. So, this is the summary of our numerical method. So we force simulations this time, but using a 2-pi periodic box with 1024 cubic and 2048 cubic grid points, so it's a rather big calculation. And R lambda is 400 something. And third order time matching scheme, third order Runge-Kutta time matching scheme. And the initial energy spectrum is 0. And we make structures, makes velocity field just by forcing. So we force horizontal velocity components and add the red noise. So it's a Ornstein-Uhlenbeck process. We integrate twice to have a certain smoothness or connectedness of velocity field. So, and we add noise in the small wave number band, K4 is 4, and K4 is 10, something like that. So we used two types of forcing. One is quasi-linear, quasi-2D, and the other one is pure 2D. I will explain this one from now. So stratification is switched after 2D flow field is produced. So, two types of 2D forcing. One is quasi-2D, which is we force just the horizontal mode, X and Y, but with different wave numbers, using different wave numbers for forcing. So, which means we have different forcing place to place. And so this means forcing component may differ vertically. And in a sense, we input some seeds of gravity waves with this forcing. So that's why we may have some contamination of artificial gravity wave and true gravity waves. So this time we use the pure 2D forcing. So for these numbers, kz is just 0, and to have just the same forcing vertically. So produce hopefully no source of gravity waves. So then gravity waves are generated by the coupling between velocity and temperature fluctuations purely, we hope. So, and to analyze velocity field, we decompose velocity field into so-called Cryer-Herring decomposition. And so it's explained simply like this. So incompressibility means gradient, divergence of velocity is 0, which means in K space, it's a U Fourier component is perpendicular to K vector. So which means U Fourier component is spanned by two independent vectors perpendicular to K. So that's why we use the two components. We decompose velocity field into two components. One is proportional to E1. E1 is just K times unit vector Z. So it's one vector which is perpendicular to wave vector. And the other one is we also again multiply K in a vector way, KZ, so which is another perpendicular direction. So E3 is just K itself, normalized by the magnitude. So these three are also normal coordinates. So we express EK into phi1, the coefficient of E1 unit vector, and phi2 as a coefficient of second E2 unit vector. And if we calculate the phi1 explicitly, so this one, E by EK times dot E1, Fourier component of U times E1, we can calculate that it's just proportional to horizontal, or actually one vorticity, which is vertical vorticity. So in a sense, we call it a vortical element. And while phi2 is calculated, then we understand it's proportional to the W tilde is a Z vector, Z component of velocity Fourier expression of Z component of velocity. So which is W is coupled with theta, so and shows very wavy structure. So that's why phi2 is as a wavy component. So this is a summary of calculation of growth of phi1. So it's a horizontal coefficient and part, and the phi2 as a wavy part. So first, we crank just 2D flow to produce 2D flow. And then after a certain time, we switch on stratification. So this is the purple line is phi1, which is horizontal. And then we switch on stratification, and the coupling begins between waves and vortices. So as time goes on, in all 4 cases, so n squared equal 10, and the forcing is 4, and n squared equal 100, the forcing is 4, forcing wave number is 4, and n squared equal 10, forcing wave number is 10, and n squared equal 100, and K forcing is 10. So all 4 combinations. So if we switch on stratification, wave part grows very rapidly, very, very rapidly, almost exponentially. So, so we believe that there's a 2D like 2D turbulence, the same 2D turbulence on any vertical slices. And so we have a certain structure, 3-dimensional structures. And so then stratification begins, and the wave part interact with such object and grows rapidly. So these, any case, it's exponential. So very rapid growth in wave structures.
Is the energy, total energy conserved?
Total, well,
it's this case
forced. It's forced. Yeah. So total energy, well, yeah. So now the growth, we like to see the growth of horizontal energy spectra. So using this energy, phi1 energy, horizontal energy and wave energy, and as a kind of diagram, and we divide time into 3 stages, A, B, C. And A is just before the wave structure begins to kind of to grow. So we see that so this is a forcing wave number, and we see -5/3 spectrum, horizontal spectrum, which is presumably so-called inverse cascade of 2D energy. So large scale is produced, and the smaller scale is -4 or -3. So it's still, there's no stratification, effect of big stratification. And then in the phase B, as wave part begins to rise, and the -5/3 2D region becomes diminished or decreased to a flat spectrum. And meanwhile, we see very shallow waves, spectra like -1 appears. So this is a kind of transient state. And later, when both waves, vortices and waves become kind of stationary, and we see flatter spectrum in the large scale and -5/3 for kind of inertial range spectrum, and we begin to see the dissipation range. So this is a history of horizontal energy spectra. Any questions? Is this okay?
I have the -5/3 spectrum in that last case, but this is an isotropic turbulence stratification.
That's right.
Still playing a strong role.
Even this is a stratified turbulence, but buoyancy effect is very much kind of packed into the large scale, and small scale it shows a nice -5/3. So
Use a tiny scale.
this, I mean, this one? Yeah, yeah, -5/3, I think so. So stratification doesn't have a very strong, well, it may, but the small scale is more dominant here.
Transition.
Yeah, so I will explain. Yeah, so now, so there are three scales, length scale, important length scale in the stratified turbulence. One is so-called buoyancy scale, so LB, which is U as either root mean square velocity, or usually it's a horizontal velocity divided by n. And buoyancy is dominant. Usually buoyancy is dominant at large scales, and n corresponds to the frequency of stable oscillations. And so this is a buoyancy scale is for large scale in stratified turbulence. And meanwhile, there's a so-called Ozumilov scale, which is a scale determined by a balance between buoyancy scale and the relation for the inertial subrange. So buoyancy scale is just U over n, and inertial subrange, which is characterized by energy dissipation, is large scale U squared divided by length scale. So if we balance, or if we equate these two, so we have so-called Ozumilov scale. And the third one is a famous Kolmogorov scale, and the scale below which the kinetic energy is dissipated by viscosity. So schematically speaking, so if we look at the energy spectrum, so large scale comes from stable oscillations, like pendulum swings stably, but and which gives a rather small nonlinearity, and that's why we have energy cascade is smaller, and we have steeper energy, -3 or something. But if we decrease the scale, and then so this motion becomes bigger and bigger, and finally tend to be overturning. So then at this scale, overturning begins, and we see transition between -c from the kind of big planetic scale, most spectrum to -5/3 Kolmogorov scale. So this the transition is so-called Ozumilov scale, and for smaller scale we have so-called Kolmogorov scale. So either 1 over LB or 2 pi over LB we have spectrum transition like this. So this is a picture for stably stratified. Did I answer to your kind of question?
Yes, it sounds like you're not actually seeing the -third regime in simulation.
Right, right. Right. So overturning is happening in that scale. Step 4.
Because then if you have more or less uniform, you eliminate the density stratification between the steps. And you might expect then the -5/3.
Within the steps.
Yeah.
I am going back to the story for the steps later, but I still have to think about that question. Anyway, so Karam Cofield, he presented the nice review papers few years ago, and these things are well documented, I think. Anyway, so this is a growth of the 3 scales in time for our simulation. And so buoyancy scale always is a, largest scale stays slight oscillations. But Ozmidov and Kolmogorov, at first t equals 0, Kolmogorov scale is larger than Ozmidov scale. But at certain time, it switched, flipped. Flipped means, so we see more transition of energy spectrum clearly after a certain time. Otherwise, it's a kind of mixed transition. Okay. So
when you see those changes, do you look at the turbulent, the fluxes in A space, and are they changing?
So
In other words, the transfer.
right. So 2D is the inverse energy cascade, and for the entropy cascade. So exactly sense. So for stratified turbulence, wait. So this -5/3 is forward cascade, not the inverse cascade.
Structure of the transfer.
Good question. I think so. That's a very good point. And changing 2D to 3D.
Right. I mean, that would be.
Yes, I agree. Thank you. Kolmogorov scale. Oh yeah, that's very interesting. So you look at the view graph very well. So actually, Kolmogorov scale, jumps, and so I don't know why, but it's a kind of breathing effect, changing structure of dissipation or spectrum, but I don't know why we observe such kind of steps. And also, Ozmidov scale has a kind of spike at this time. So there might be something, but we haven't identified. You mentioned the stairs. Is this one?
Well, I mean, trying to relate it to what Colton told us again, you'd expect a step and on the flat bits.
Yeah.
You'd expect more likely as a tropic type.
So yeah, this event happens rather, I don't know which scale this happens exactly. I haven't checked. So yes, and thank you anyway. So here's a development of horizontal layers. So again, using this energy, growth of energy as a guideline, we plotted the kinetic energy in each direction and total energy. So at first, of course, velocity in the z direction is almost zero. So we see some fluctuation in x and y, but total is something like that. But then, so this is a horizontal. So this is vertical direction. So it's a horizontal average of kinetic energy. So if we look at the vertical layers, or actually horizontal layers, we see some part becomes shows peaks, and so peak grows, and it's very interesting. But just the energy looks concentrated in one direction. So in one direction, for example, this is x direction, x, and meanwhile, y direction is very small, and y energy or x energy is almost like total energy, which means energy is concentrated on maybe one direction. So zigzag is kind of nicely one direction. One direction is so vortex dipoles are propagating, and so zigzag happens in the direction perpendicular to the translation always. But for our case, it looks like more like spikes. So one direction, it shows some jet or something happens. So we may have kind of different ideas or views from zigzag instability or zigzag vortex. So same is true. This is a temperature fluctuations. So again, purple is the horizontal energy, and the green is temperature fluctuation divided, or actually z derivative of temperature fluctuations. So temperature fluctuation shows very spiky, sharp peaks or spikes as time goes on. And we are concerned with the spacing of spikes or temperature derivatives, vertical derivative of temperature fluctuations. And so this is a length which corresponds to 2 pi u over n is a buoyancy scale. So which agrees with perhaps Karam-Caulfield's observation or theory. So the spikes, the intervals is proportional to buoyancy scale, large buoyancy scale.
In your previous slide,
Sorry.
when you go
Yeah.
you seem to have an indication that maybe selecting the four is it somehow
you mean depending on the forcing? Yeah, well, I haven't checked it, but forcing is rather kind of isotropic and nothing to do with the forcing, I believe. But k equal 4. Yeah, okay, I see. So this is k equal 10, and k equal 4 is similar, I think similar spikes. So nothing, well, in particular, this is z direction, and forcing is always horizontal. But thank you, that's a good point. So here's one snapshot of temperature fluctuations in a vertical plane. And so to see the structures, I plotted with grayscale. And so white is temperature fluctuation is large and plus, and black is negative. So looks like very much, well, we see some layers, but looks like just turbulence. So so white line is so I monitored temperature fluctuations along this line. So this is a temperature fluctuation along that white line, where we see more kind of layers. So and it's very interesting. But so we see some slow oscillation, but in one direction it is rather flat. So we say that I think it's not symmetric in the vertical directions. So we say it's a sawtooth wavy jumps. And the meaning is if we superpose with Brandt-Weissler curve or Brandt-Weissler straight line, we see some clear stairs corresponding to this jump, big jump. So these asymmetry in cooling and then big jumps in warmer direction. So anyway, so we say it's a cliff. Cliff is just a cliff, and ramp is slowly moving. So we see cliff and ramp structures coming from these asymmetry of these things.
Getting back to your point. Some timing, commonality in timing, synchronization in forming the layers. The spiking brings the idea of they're independent. So the question is, when these things start forming, are they at sort of simultaneous, or is it more sequential?
We believe that so this data is coming from the kind of snapshot. So your question is when these structures appear, and we believe, we haven't checked it exactly, but we believe that the appearance of these things is relating to the previous spectrum, when spectrum changes phase. So actually, after these things happen, then we.
Of course, for those things to form, it has to know about stratification, which means the spectrum would have changed.
Right. We haven't identified when exactly, but so yes, and so this is just one snapshot and one sample line. But if we look at the PDF of temperature fluctuations and its derivatives, clearly, so this is a whole domain. And we see temperature fluctuation is pretty much Gaussian. That's fine. But X derivative and Y derivative are symmetric. But meanwhile, Z derivative shows skewed. Z derivative shows skewed means, so we see a higher possibility of finding positive slope or bigger positive slope than negative slopes. That explains the asymmetry in the rising and well, I think I wonder, well, anyway, let me continue. So the possible mechanism to produce such structures is we see warm air above cold air, and between the two, there's a, sharp interface. And in the cold air, it goes up, goes down, but suddenly warms up. So this is what is happening schematically, but we don't know the reason yet. So, and there's a other kind of asymmetry in the cold and warm area. So this is a conditional PDF of entropy. Entropy is a magnitude of vorticity. And for temperature, fluctuation is positive. It's a conditional, just positive and just negative. They give the same conditional PDF of entropy. But if we look at the derivative, it's very big. Temperature, the derivative of temperature fraction is very big, 6 sigma, bigger than 6 sigma. Then we see asymmetry, or actually theta is negative, is larger, probability than theta is positive. So which means in the region of strong vertical gradient of temperature fluctuations, entropy is stronger in the cooler temperature than the warmer. And vorticity, in that sense, vorticity is larger in the cooler regions. Is it true or not? I'm not 100% sure. And why I'm not sure 100% either. But we see that the cooler region, stronger nonlinearity, or either vortex stretching, or alignment of vorticity with velocity or velocity gradient, or vertical structures. And so we searched kind of first vertical structures near the jumps, but we couldn't identify such a large scale vertical structures. So other things, other possible candidates, stronger nonlinearity or stronger alignment, we haven't checked it. But one suggestion is, so this is a vertical temperature derivative versus helicity, and averaged in horizontal planes. So, so this is purple is helicity curve, averaged, you know, in the horizontal planes. And this is again, green is a temperature gradient. And at least helicity, a possible source of asymmetry, at least has the same vertical scale with the vertical temperature derivatives. But we can't say more than that. So helicity might be a, you know, reason to produce such kind of asymmetry, but we don't know.
Is there a correlation?
No, I haven't checked. So maybe correlation. Yeah, we can check.
Comment on Chokesek, the emergence or formation of helicity. What is setting the origin?
Good. So I'm not saying that helicity is a source, but anyway, so we don't know which is cause and which is effect. So anyway, they are correlated, but we don't know whether it's a source or effect yet. So I'm sorry. So this is a summary. What time is? Yeah, okay. So this is a summary. So strong temperature fronts are produced quickly in phase with the growth of gravity waves and horizontal layers. The width of strong temperature fronts is scaled as U over N, sorry, buoyancy scale. The structure of temperature fronts shows vertical asymmetry. The reason for the mechanism for the asymmetry is still open question. So thank you very much.
Yoshi? More questions? It's something important. Do you have a Prandtl number?
Prandtl number is 1. Yeah.
But in terms of your picture, it's from
Yeah. So, but changing the, we can tune moderately, but we can't produce, you know, very high or very low numbers. Perhaps it may be difficult. I don't know.
Yoshi, so you chose one line at one time. If you average horizontally and time average, does everything still?
So
you kind of chose the best.
So well, so other lines, yeah, presumably. Yeah, but yeah, but so we chose this line as a typical, you know, place where yeah, it's the best. But to say some you know, support, we calculated the, you know, whole PDF in the whole domain, So it's asymmetry, you know, skewed, which shows which support. So higher temperature is the gradient is bigger. Yeah.
So to ask the obligatory question, as the layers develop, do you see any indication of mergers or coarsening as time evolves? As time
Merger or forcing?
Or coarsening. In other words, layers coalescing in one form or another. For example, Caulfield was talking about shear abilities in the jumps, basically driving a kind of merger event. Any sign of this, or is it perhaps comes later in the story?
I think it's a very natural process to have such things, but then I haven't identified the. Okay. Thank you.